Hello guys, today we're going to be talking to you about the Aurora Borealis. And so the people who worked on this project are myself, Alex, and Reed.
First of all, what is an aurora? An aurora is something almost everyone has seen, at least in movies or pictures. It's a natural light phenomena which happens in the sky. It can be seen in different shapes. It can be rays, surfaces, circles, spirals. And whenever it shows itself, it could be in the colors of green, yellow, purple, orange, and this is due to the photons being excited at different wavelengths.
So like Alex mentioned, we usually think of auroras through movies, but it's important to know that the auroras exist like on the Earth's poles almost all the time. And so depending on where you are either going to be experiencing the northern or the southern aurora ovals because the auroras usually form as continuous rings around the Earth. These rings usually also expand about 2,500 miles.
So where can you find an aurora? On Earth, they most often occur at an area surrounding the geomagnetic poles. The aurora in the northern hemisphere is known as the Aurora Borealis, while its southern counterpart is the Aurora Australis. They're not specific to Earth, however. In fact, they can occur on any planet with a magnetic field and an atmosphere.
One of the main one of the main contributors to the auroras is the sun. In the sun, we have helium atoms, and they undergo to some process of fission. They exert enormous amounts of energy, which go in the form of plasma. When they travel all the way through space and hit Earth, that's what we call solar wind. Uh, they affect the Earth's magnetic field, and they're usually made of protons and electrons coming from the sun's corona.
So solar wind usually like fluctuates according to what we call the sun cycles. If you look to the picture on the right, you can see that we have a lot of years lined up, and then on your y-axis you have sunspot numbers. So this is almost how we kind of can see that the sun activity fluctuates as time progresses. So solar activity is kind of what changes and fluctuates solar wind. In addition to that, coronal mass ejections and solar flares also affect the behavior of the aurora. If you look at the picture at the bottom right, you can see what a coronal mass ejection would look like.
As we know, charged particles interact with the magnetic field. When charged particles from the sun near the Earth's magnetic field, they'll experience a force. Charged particles from the sun will interact with the Earth's magnetic field and respond accordingly. Depending on the charge of the particle and which magnetic pole the charge is near, the particle may be repelled or attracted. Since the Earth's field is perpendicular to the Earth's surface near the poles, these particles will move towards the Earth's surface at these regions. An example of how these particles may interact with the field is shown in the image.
And so whenever the charged particles are heading towards the Earth, they're usually traveling at about 400 kilometers per second. But by the time they interact with the particles in our atmosphere, they're traveling at about 1/10 the speed of light. The way that this increase in velocity occurs is through a process called mirroring. So whenever the particles are incoming into where the geomagnetic poles converge, so at the north and southern poles, they experience a stronger magnetic field. This magnetic field repels them and attracts them simultaneously. This process of simultaneous attraction and repelling is mirroring. And so the repulsive force almost behaves kind of like a resistor, right? So we can think of the current that is being carried by the charged particles and the effective resistors as a circuit. And we can also think of it as there being a voltage concentration around the poles. This voltage concentration is what then accelerates other incoming particles from going from 400 kilometers per second to 1/10 the speed of light.
Whenever these particles they reach the atmosphere, they encounter several other molecules which consist of the atmosphere itself. Some of these molecules are going to be the nitrogen, the oxygen, and the ionized nitrogen. Once these particles come in from the sun, they uh, they collide with these other molecules and they excite photons in different wavelengths. We can see over here an energy chart uh, showing the relationship between the wavelengths and the molecules as they're being excited. Another of the factors which contributes to the color of the aurora is the altitude. The altitude, it shows the distribution of how these molecules are shown in the earth. For example, from 80 kilometers to 100 kilometers, we see a majority of nitrogen particles. From 100 to 250, we see nitrogen ionized particles. And above that, we see the oxygen particles. Uh, the color of the auroras, it all depends on where they are located or what is the density of these molecules in the atmosphere. And this is controlled by several meteorologistic factors, such as the atmospheric pressure or solar winds.
Now, you might be asking yourself, how do we measure the aurora? And so the way that this happens is that scientists combine ground videos of what the aurora look like, along with satellite information of the energy and the total number of charged particles incoming into the Earth's magnetic field. And so what they do is they combine both of these sets of data to determine what energy and what number of charged particles corresponds to what behavior. And so ultimately, what we end up with is almost kind of like information that tells us this amount of energy and this amount of particles is going to give us behavior that looks like this. And so that's one of the ways in which we measure the aurora.
Using that data, systems have been set up to forecast the aurora. All of the contributing processes are predictable, similar to weather on the surface of the Earth. These systems will predict factors such as the solar wind, the geomagnetic activity, when the aurora will appear, where it will appear, all while primarily using data from the sun. Most of these factors are dependent on your location on the Earth's surface. A lot of this data is accessible to the public and is updated in real time. One value used for prediction is the KP index, which is used to refer to geomagnetic activity for a 3-hour period. In the image on the right, you can see different KP values for different latitudes.
Okay, this has been the presentation for the Aurora Borealis, and here we have the citations page. Thank you so much for your attention.